Hello everyone, nice to see all of you here today. And I would like to point out that if I'm not mistaken, this is the first event from the webinar series of JACOV Community in 2024. So basically, Happy New Year, everyone, for the ones who haven't joined our Genius Talks yet. And by the way, a short advertisement note in case if you're interested in more events and news from the Java world, please do not miss our Genius Digest, which comes to your email boxes regularly, and this month it will come to you soon, as well as do not miss our Genius Talks, which we also conduct regularly, and we will be really happy to see all of you there to discuss this amazing news from Java world. And as for today, this is, as I've already mentioned, one of the first webinars this year, and we are really happy that we are going to discuss some interesting and technical stuff which will be useful for all of you guys, I hope. And today it will be aspects of microservice interactions. So as for our communication channels, please do not hesitate to use our chats on OrgJaCommunity platform as well as comments on YouTube if you're watching us there, to post your questions, and we will try to handle them during the Q&A session with our amazing speaker. And also, in case if you're interested in rewatch of this recording, please don't hesitate to visit our page on OrgJaCommunity platform for this talk. So, long story short, I think we're ready to go, and let me introduce you to our speaker, Oresztesz. Hi, and the floor is yours.
Hello everyone. Yeah, so let me zoom in a little bit. I think you can see my screen now, if everything's okay.
Yep.
Yeah, and as it was heard, today we are going to talk about the aspects of microservice interactions, and I will just jumpstart right into the topic if that's okay for everyone. Yeah, so first question, actually it's a valid one. What does that start do in the title screen anyway? So the reason I chose this title screen is because when I was started working with microservices and studying this topic, they were also often referred to as Death Star architectures. And one of the reasons for doing so was these strange interaction diagrams that you can see on the screen. So when you look at the way microservices communicate, when you try to generate these interaction diagrams, they show the increasing complexity of the communication. So actually, one of the biggest challenges of this architectural style is network communication. And that's why in this talk, we are just going to focus on that. So all the topic will be just investigating this thin line that goes between two microservices. There are also many valid ways, of course, to introduce any kind of dependency between services, between microservices. But this is the most flexible one and the most commonly used one. So that's why it has the biggest effect of our whole architecture. And in this talk, I would like to go through the so-called driving forces that are going to affect this communication line. And also at the second half, we are going to go through several practical examples I observed while working with services, and also show you how we improve the communication with these so-called tools, with our toolbox that are basically just a bunch of buttons and practices. Yeah, so as the first half of this topic, let's talk about the driving forces to understand what we need to optimize, what are the things that actually are affecting this communication channel. So first thing is latency, of course. Availability was also something that's very important. There's reliability. That's talking about the stability of the whole communication channel between the services, which is quite unreliable. There's this thing called queuing theory, which is what I found is rarely examined. So I would like to just give you a brief, gentle introduction into queuing theory, and later on discuss how we use queuing theory to also improve our interactions in one of the use cases. And there's also the human factor, which I try to cover with this thing called Conway's law. Yeah, so what about latency? Latency has a physical limit that's bound to the speed of light, right? So nothing is able to go faster than the speed of light. It's quite obvious. Actually, speed of light is not a constant value. So speed of light is also determined by the density of the material it's passing through. So the picture that you can see on the screen is basically from a simulation that shows the theoretical round trip time between two locations. So if you look at the two coasts of the US, you can see that the round trip time in vacuum in the bottom right is 27 milliseconds. That's the minimum time you have to spend on just sending a very small packet from one point to the other point. But the problem is that the realistic round trip time is also going to be much slower if it's passing through fiber optics. Reason is that fiber optic is often a more dense material than vacuum, of course. So a more realistic value, which is still just a theoretical value, is 41 millisecond. There are several statistics and several numbers on how each cloud provider performs in this race of round trip time between two locations. Actually, practically, this number is at minimum 50 milliseconds. What does this tell us, and why is it so important? So it's getting more and more common to have two cloud locations or two regions in a cloud deployment. So usually nowadays it's very rare to just deploy and operate everything in one single region. And these regions have to communicate with each other. A very common use case is just to synchronize data between the regions. Because otherwise you could not do region failovers, right? So in if you don't do data synchronization, and if you lose a region, then all your users cannot go into another region to continue their workflow. And the data synchronization is bound to this upper limit of the round trip time. So this will be at minimum 50 milliseconds. But in practice, because workload is stockpiling up, after you put more and more pressure on that specific region, this is practically going to be a value between 500 milliseconds to up to several seconds, and the minimum value or the idealistic value is just 50 milliseconds. And you have to calculate this and into your performance numbers if you want to deliver very low latency responses to your clients. Then you can serve them from one single region, but if you have to go to another region for any reason, for synchronization issues, or if you plan to just fail over to the other location, you should expect at least 50 milliseconds of delay in terms of data synchronization. But there are other also practical use cases that are affecting latency. Of course, this is the most common one. So how does latency correlates to throughput? Let's say so. There was a study that was trying to that was examining the correlation between latency and throughput. One of the numbers they measured is the page load time, which can be translated into at least 100 requests. So it's 100 round trip times aggregated, and there is on this bottom of this chart is bandwidth, which is basically can be transformed into the throughput of our architecture. And as you can see, actually, as you increase the bandwidth, the benefit from increasing the page load time diminishes over time. So after you multiply it more over and over, you will get less and less benefit in terms of the page load time itself. So if you translate this also into practical terms, we can say that scalability does not really affect the latency. So it doesn't matter if you have auto scaling in your cloud infrastructure, you are not going to get better latency numbers at all. Maybe in the very beginning, you might see some speed up from scaling out, especially if your current infrastructure is really struggling with the current load. But after a while, it's just not going to solve your problem. So if you just try to ignore latency because you're saying, yeah, we are auto scaling, everything should be okay and automatized, that's not true. In correlation with that, if you try to investigate the decrease of the page load time depending on the round trip time, you can see a linear scale now. So what does this mean is that if you have better latency, of course, your page will actually load up linearly faster because it translates to roughly 100 latency, 100 requests and the latency of those requests. Yeah, so talking about availability. So availability is determined by one single thing. That's the dependency graph of your architecture. So each component individually has an availability number attached to that. So as you can see, for instance, in this graph or this diagram, which is just a theoretical machine architecture, if each component has 99% of availability, the combination of this directed graph also shows an availability number that can be calculated by just statistical formulas. And this translates into just 96% of availability. But there is no such thing as a single machine architecture. So if you, let's say, zoom out and see this client server model, now we have multiple components and each of them depends on each other. So for instance, in this case, a successful transaction that's coming out from the client needs both parties, the client server and the database, also respond successfully. If each component has a 99% of the chance of doing so, you can calculate again the aggregated overall availability. And this just now translates into 88.5%. So what does this tell us? Yeah, first of all, if you introduce, as a simple rule, if you introduce a new dependency of your architecture, then it's guaranteed that the availability will be decreased because you cannot depend on something that has 100% availability, of course. This number is less than that. And also the availability itself will be affected by the outbound calls. So if you reduce the number of outbound calls and introduce a different kind of dependency, if you are lucky enough to do so, then you will have a better number. And also another thing that I want to mention is that availability can be calculated. So if you have a high level dependency graph of your target architecture, for instance, you can go for each service SLA, a service level agreement, investigate that number that gives you a rough estimate on the target availability and use that for your calculation and aggregate a number from that. Okay, now what we can say from reliability is that reliability really has some special use cases. So we all think that, yeah, TCP communication is reliable because we have these acknowledgements and resending packets and so on and so forth. But even TCP is an unreliable protocol because if we see just a single request response between the client server, it can fail in various ways and the client doesn't have an understanding on how to proceed from. So for instance, we can just simply fail while sending the packet or sending the request. In this way, the client can just simply resend the request, right? But we can also fail on the server side by processing the request, and also fail while after the server was successfully processed the request, but when it's responding to the client. And in this way, the client, let's say, has a timeout value and just retries and sends the write operation over to the server again, then the server really does not know why this happened, or a client does not really know that the write was already done, and you can transition into this inconsistent state that's hard to recover from. So that's why, for instance, you have idempotent operation. That's why exactly once messaging semantics is quite difficult to implement, for instance, because if this is a messaging protocol and the server just acknowledges the message that it consumed successfully, if this acknowledging fails, then the client just will simply resend the event or the message to the server side. That's the most common way of recovering. If this is a database write, then, for instance, then the client needs to reinitiate the operation. If it's done in a single transaction, that's okay. But if this is a distributed transaction, like a two-phase commit, then and if we are in the commit phase, then the client does not really know where to recover from because it just sees the failed response, but commit for some of the nodes is already done, so does not know how to recover from the situation. So this, I think, very well shows you how these kind of client-server communication scenarios become really complicated, and that's why some of these distributed protocols like messaging exactly one semantics and two-phase commits failed in the past, and that's why we are trying to rely on eventual consistency instead, because network communication is unreliable. Okay, if we again zoom out and not just investigate single requests, we can also see that statistically we are not really in a stable situation. So let's say we have theoretically a single request which has 99% of chance of succeeding. Okay, so a single request has now overall 99% of the chance to succeed. What's with 100 requests? So if you remember, for the case in the page load time, 100 requests is roughly the equal of loading a full page if you have many elements. So for 100 requests, statistically, because you have several permutations of failure for those 100 requests, the overall possibility of succeeding is just less than 40%. Again, just because the statistics is against you. So that's why, for instance, investigating long tail reliability like 99.99% percentiles and so on and so forth in some situations are quite valuable. So this, what I talked about briefly, manifested in a few artifacts I commonly know and use, not on a daily basis, but when at least discussing about these topics. One of these things is this artifact called Latency Numbers Every Programmer Should Know. In this version that I use, there is also a slider. You can set up the year with this slider and investigate how these numbers changed over time. This helps you understand better your design choices. So, for instance, should we use an in-memory caching or some distributed cache solution, like Redis, for instance? These numbers can give you a hint. So if you look at this main memory reference in the top left side, you can see it's 100 nanoseconds. If you look at in the middle, in the center, you will see round trip time in same data center, which is 500 microseconds. So you would say that, yeah, 500 microseconds is a very, very low value, should not affect or choices at all. We should go with this choice. I mean, why should I care? But if you see the difference between these numbers, one of them is 5,000 times faster than the other. So if you have a very, very low latency baseline to meet, in some cases, it might help because if you count with thousands of requests, these numbers adds up. So it might help if you choose in-memory solution instead of going to the network channel again and getting the data from somewhere else. Yeah, and the other one is these fallacies of distributed computing. There are several ones listed, and there is also description for each of them. I see this from time to time, even in LinkedIn. I think it was posted by someone in past week with some nice diagrams. So if you see just the top three, we covered the top three already. So reliability, latency, bandwidth, throughput, scalability, and so on and so forth. So I encourage you to also investigate the others and also understand the effect of your on your architecture or the other fallacies. Okay, now with queuing theory, I would like to go with some practical examples in the next section because I think that's very, very important. And for in my experience, for some of us, it's quite an unknown topic. Okay, so if you investigate a simple model of a queue with an executor which is this blue box, you can see that usually it's worth talking about these numbers here that you can see on the screen. Arrival rate is the rate of the orange marbles arriving to the queue. Latency is the number or is the duration of a orange marble being processed and then translated into this green marble on the right. Departure rate is the rate of these green marbles produced by the system. And then you have this execution time, which is the time required for this blue box to produce the green marbles. Okay, so what should happen when the arrival rate is higher than the departure rate? This is often a situation that's happening because everything is published on the internet and we don't really have control over how many um, people have access to our services. Let's say we have a public facing API or something similar. If we don't do something, then we're screwed, right? So there's no scalability setting that will help us survive this scenario. We have to introduce something between the two. So this is obviously something like back pressure or rate limiting. That needs to be done. That's something that we should not forget. So I believe that rate limiting and back pressure is the second most important configuration to tune. Let's say it like that. Configuration to tune besides timeout. So okay, let's go back into the simplest scenario we can think of. We have a single queue, we have a single executor. Let's see all these numbers that we talked about. So what should be our throughput or what should be our departure rate? So we are producing a single marble in every 100 milliseconds. So if we sum up, then we are producing 10 marbles per second. The latency for a single marble is 100 milliseconds because that's the required time from the left side to travel to the right side from a single marble. If we don't calculate in the length of the queue itself. What if we now scale out our infrastructure? So we have now two executors. Each of them has the execution time of 100 milliseconds. On the right side, we can see that now, yeah, the throughput is doubled because we are now producing 2 marbles in each 100 milliseconds, and that's 20 marbles per second if you multiply it. The latency for a single marble is still 100 milliseconds. So it does not matter how much we scale out, the orange marble has to wait at least 100 milliseconds until it's being processed and being transferred into this green marble. All right. Okay. And what if I introduce a pipeline with multiple operations? So what if we split up this 100 milliseconds of execution into and have two subcommands, let's say, or two parallel operations, and don't do it sequentially. Each of them, let's be fair, and let's say that each of them is now processing the marble in 50 milliseconds. Okay, so in the first 50 millisecond time interval, we process one marble into the other queue. And then the next interval, we now successfully created a green marble. So we are processing a green marble in every 100 milliseconds. Then the way time is passing by, this goes on and so on and so forth. And in each 50 millisecond, from accepting the first phase when we haven't had any orange marble in the right queue, we are producing a green marble in every 50 milliseconds. So this tells us that, okay, the throughput is again became better because now we have 20 marbles produced in each second or in each 50 millisecond, except for the first 50 millisecond interval, we can produce a single marble. But the latency is still going to be 100 milliseconds because we have to go through both executors, which is 2 times 50 milliseconds. Again, latency is not really affected from the perspective of a single marble if we really just investigate the optimistic value and don't count in the queue length, but the throughput is again doubled. So if you think about things like the reactive libraries or similar libraries, when you have a declarative way of splitting up your workload, and even though what you see is sequential, but it's executed in separate work queues, you will see an increase in the throughput or in the performance will get better, regardless of your declaration being just sequential. So that's the magic of the reactive library. One of them, let's say it like that, that you can split up your workload and declare it differently, and it will actually create a parallelism. And latency is not really affected in this case still. So that's an important thing to mention. If you have a bottleneck, so let's say if you have an executor that has a single that's processing the every marble in 100 milliseconds and just choking the whole performance, then you will see that the throughput for in this case is going to be 10 marbles per second. Why? Because the bottleneck, these 100 millisecond execution is determining your throughput really. So you are going to just produce a green marble in each 100 millisecond time frame. The latency is going to be still the sum of all the executors. So for a single marble, that's going to be 150 milliseconds. If you want, you can translate this into formulas. What's really important to mention, I think, here is that the latency itself still is not necessarily going to be determined by your number of executors. It's just going to be determined by your execution path, and all these execution times just summing up. Yeah, for the throughput itself, that's going to be affected by your infrastructure and by scaling out. It's going to give you more performance if you scale out your infrastructure. What's the other benefits of using queues? One of them that's very valuable is separating by quality of service into separate channels. Your workload actually into separate channels. So in this case, what you can see on the screen, the producer, which is producing the orange marbles, is choking the performance of the whole system. It's a bit difficult to see, but you can see that the arrival rate for the orange marbles is double than for the other marbles. And actually, this will take valuable execution time from the others. So one of the approach for recovering from this situation is just separating on each channel based on the kind of work you would like to process into separate queues, and in this way the arrival rate of the orange marbles is not going to be affecting the arrival or the execution time for the others, because it's now in a separate channel. So if it tries to choke the performance, all the green marbles can still proceed if you have a separate your executor attached to them. So this is used in various ways in a microservices architecture. One of them is used also in rate limiting. So you can do rate limiting like that. Other one is just separating your workload and focusing on a single workload on a single service. So if you think about that, usually microservices are focusing on a single kind of workload, and you have a separate scalability rule attached to that focused workload. And that's why it can perform better in terms of scaling, because if you have more orange marbles arriving, you just have to scale out the top executors. The other can not necessarily has to be affected by those. Okay, now what's with Conway's law? Sorry. Yeah, so in Conway's law, I think what it really tells me in brief is that you don't you cannot ignore actually the human factor from the whole equation. So if you have a communication channel between two services, you need to consider the teams which are maintaining these communication channels. If you have a single team on both ends, this is the most flexible situation, because you can do whatever you want to, right? So there are other scenarios as well, like this, which is probably an anti-pattern. Like if you have a common team that's either operating the client or the service, then because it is a shared responsibility, then things are not going to proceed so fast. So if you expect a breaking change to go through, um, in this practical scenario, you cannot expect it to be done very fast. Now, there are other situations, like for instance, you are sitting on the provider side and the clients are sitting, which are multiple teams, are sitting on the other side. What you should remember, what's the most important thing, I think, if I need to sum up, is that the schema ownership does not necessarily sit on the same side. Okay, so there are techniques which can help you to transfer the schema ownership to the other side, to these multiple teams. And in this way, they will maintain the schema, they will define and declare what do they need. And you as a provider, you just need to comply with their requirements. So for instance, you can do contract-based testing. You can introduce strongly typed schemas. If you, for instance, use GraphQL or some other schema validating and versioning frameworks that can help you transfer the schema ownership on the other side, and clients declare your schema and validate your current version of your current API with the schema they are demanding. And this is something that's not just a nice to have, but this is something that you need to have if you have multiple teams on both sides. So think about event-based microservices. So this is a more complicated scenario. You need at least some sort of a schema management, even better schema federation sitting between both sides that help you to verify the payload, to help you version your current schemas and help you manage that with multiple teams. Yeah, so getting away from the first part, I say that simply for every team there is a specific toolbox with well-known patterns and practices that helps you to deal with the things that we were mentioning before. So I would like to just briefly go through the toolbox that are covering the most of the things that I was talking about, or I will talk about in the second half, and we will just zoom into the practical examples. So what are these? CQRS is the first one that I would like to mention. This is simply command query segregation. So responsibility segregation, sorry. So splitting the two communication channels, splitting read and write related operations can help in some situations. Even if, especially if you look at the non-functional requirements, then it can, I think, gradually simplify your solution and help you perform better. We talked about schemas in the previous section. I was talking about Conway's law. Caching is something that introduced in every layer, I believe. You have to be conscious about your caching solution, your caching strategy overall. And there is some technique called multi-writes which help you keep the cached values fresh. You can proactively write the up-to-date data and don't have to wait for time to leave to happen. And that's what I just simply call multi-write. I've met this in a presentation. There are other techniques for changing from asynchronous to synchronous communication, or from other way around, from asynchronous to synchronous. This is sometimes necessary to do just to comply with the existing mechanism of your APIs. There are also design techniques like cloud native, 12-factor. I think it's good to mention those. Auto scaling, we talked about a lot. Back pressure, again, I think I mentioned it several ways in the queuing theory section. You need a higher level of let's say, loosely managed transactions. Most important aspect of this was the reliability section, and I think two-phase commit. You need something that's a long-term transaction, and you need to introduce orchestration or choreography. Service mesh is important because many resiliency patterns can be introduced also into service mesh with simple configuration. you need to be actually conscious about your technology choices. For instance, GraphQL can perform better than REST because it has less round trips, because the packages are smaller and more condensed than a REST call. You can give to your architecture more throughput, for instance. There are tons of messaging patterns. I won't talk about this in detail, but if you're doing asynchronous communication, then you feel free to use those as well. The chosen concurrency model can have a positive effect on your infrastructure or your communication in the application, because you can introduce a higher level of parallelism. So if you go reactive, or if you use coroutines, other stuff, then you can expect better performance and more resource efficient processing. Resiliency patterns, I think, are the most valuable and most known ones. Most important is timeout, because it's set to 30 seconds by default in every libraries. But retries, circuit breakers are also quite important, I think. And don't forget about back pressure. And you have to have observability, of course, to see the effect of all of these and to be able to improve all of the things that I mentioned above. Now let's jump right into examples. The second half. As a warm-up, one of the nice approaches that I've met in a Cassandra database was this thing called rapid read protection. What's happening? So without you knowing too much about Cassandra, it's a distributed database. It needs to keep the data up in sync, actually, between all these nodes that you can see on the right. So if you have a read request from a client, it needs to reach out to several replicas based on the data it's being accessed. Um, so the client goes into a coordinator node, which is this node on the top left, and that node finds the actual replicas for that specific data set and tries to aggregate the response to make sure that it's up to date based on um, different values. Now, what happens if one of the requests just being slow? Should we wait for that specific request, or that response and just time out, or do some other approach? Actually, what Cassandra chose to, yeah, sorry, I need to go back to the slide. I pressed the wrong button. I think, yeah, it was that. So actually, instead of Cassandra just choosing to wait for that response, it just fires up a backup request. So instead of just relying on timeout, it proactively goes to another replica, hoping that that value will arrive earlier. And why should it do so? So if you think about availabilities, let's say again, then let's have a simple scenario. Each node should have 99% of availability. Now, if you just rely on the next replica, then your availability will be just, or for the single request, your availability will be just 99%, of course. But if you hit that 1% failure, if you go into the with this backup request to the other node, your overall availability will increase. So your overall availability for the single request will be more like around 99.99% just because of statistics. And also, if you look at those long tail kind of error rates in a Cassandra cluster, that's why it's going to be performed better, because in these failure scenarios, you will have less error rates actually. Okay, in another situation I've met, I had to create very simplistic services that were attached to a key value store. In this case, let's say it was DynamoDB database. It had a quite read-heavy workload. The writes did not really change, so it was just simplified down, and it was just creating data that need to be read on the other side. But it had a quite tight, low latency requirement, and that's why cold cache and distributed cache solutions were not really performing very well in this situation. So what helped here is actually splitting the writes from the reads, so applying CQRS in this case. Writes became asynchronous, so they were not even going directly to the database. They were collected by a simple queue service. This way, reducing the write performance DynamoDB had to be configured to. And for the read, to meet these low latency requirements, I introduced an in-memory caching solution, which was also proactively replicating between each other. So the read nodes did not really wait for cache miss to happen. If there was already a cached value for in the other read nodes, which were accessible on the same cluster, they were proactively started to replicate. And that's how I address multi-write in this situation. So in the in-memory cache itself also helped in two ways. So actually it helped with the latency, and it helped keeping the cache fresh because and also reducing the reads hitting the database because it was also proactively synchronizing between each other. So this helped me actually drastically reduce the latency requirements for this specific situation. Okay, so just as a side note, client libraries. I think we have to mention client libraries in terms of microservices because practically I think in every scenario I've met, there is also always a set of libraries which are commonly used in each service as a default, and teams often use that to aid creating new services and to speed up the development. And I think this practice is quite grown controversially. It's often a double-edged sword, mainly because those teams which are creating these client libraries not very experienced in library development in general. So they learn along the way while creating these libraries, and there are many issues I faced while using just a single common dependency on all the client libraries um, in each services I touch. So in this specific situation, the following happens. So the service itself needs some metadata at startup, and this client library automatically was attached to the startup process and started downloading this metadata, and it was a zip file containing all the metadata for all the services globally. Um, and it, during initiation, unzipped the content, and this unfortunately messed up the whole startup process for the service itself. And there was no configuration to turn it off or to disable it for development. So for development purposes, all the startups were messed up, which were using this monolithic client library in this use case, unfortunately. So yeah, it was quite tough to resolve or overcome from the situation. Even worse, in some cases, also it's also messed up the health check or the readiness for the specific service, because if the data was not ready or it was not accessible for some reasons, then the startup failed for that service. Also, deployment failed because it failed to show that it's ready to the container orchestrator. So the deployment was rolled back in these situations. So solutions for this case, one of them is just shifting left the whole thing. How we can shift left in this situation, in this whole mechanism, because S3 is relatively easy to mock out. You can do something like a sidecar container that's complying with the protocol. Just use a mock data that's empty, or just use a zip file that has just minimized content and use that for the pipeline. Even you can ship it with this minimized data set with as a sidecar container during your deployment. And because it's accessed locally, you don't have this issue with rollout and rollback if the data is not accessible. In other cases, they use a proxy, which had some fake operation when the data was not readily accessible. All right. Now, I would like to talk about another practice that I haven't found an official name for. I call it region pinning. I met that when we were doing Cloudwine migration and when we were transitioning from single region deployment to multi-region. And the important thing was that the client held a state that's similar to a shopping cart in this case, which had to be strongly consistent. So if I move the client holding the shopping cart in the mobile on the other side, on the other region, then this shopping cart should not be lost, should not be altered, changed, and so on. But the problem was that if you try to just pick users and move them to another region, to test the deployment on the other side. And if you go across the red line on the bottom, this has a replication lag. And you don't really know when the data will be there and if it will be consistent or not. You don't have control over that. You know that it's going to be 50 to 60 milliseconds, but it can be up to anything, right? It's much easier to just go through this region boundary that's simulated by this white dotted line in the middle and pay the 60 millisecond penalty. But if you try to pay it for all the users, it's going to kill your performance. So you have to be creatively selecting the users which need the 60 millisecond penalty, but the others should not be affected really. And that's how region pinning came into place. It was controlled by a simple cookie which told the users the originating region when they created the shopping cart, let's say it like that. So when these specific users were moved to the other side, they were also sending the originating region as a cookie, and the client library that was working well. In this case, it was not a double-edged sword. Was instead of going locally and relying on this replication lag for the cluster, proactively reach to the other region, paying for the 60 milliseconds penalty for those selected users it needed to. And I also discovered that this pattern actually helps you solve other interesting scenarios. Like, for instance, we were designing an auction site, and there was also auctions initiated, which needed to keep the bids that were sent to the site sequential, right? If you have two Kafka clusters trying to um, collect these auctions, if you start writing on both regions, then it's not the sequence itself is not going to be guaranteed. There is replication between the two, but it's asynchronous. So simply you just have to select the initiating region for that auction, and everybody else who is trying to join from the other region can use the services, but not the locally provided data source. It had to go back to the originating one. And for instance, this is used quite common in gaming. If you think about that, there is always an originating server. It shows you statistics on your current latency. If you want to join some game on the US, you have to pay that latency penalty. There is no overcome from that. All right, so in the last part, I'm going to talk about the several improvements for a single service. So bear with me. And we use several practices mentioned before to improve the reliability, the cost effectiveness of this single service. The baseline is this one. So we had again DynamoDB on the two DynamoDB tables actually on the storage side. This was a simple key value store with a twist. So you can see a values endpoint that helps you read values for a specific key. But on the left side, you also have another endpoint that has a statistical meaning attached to that, that shows you the keys that were used by this specific client that was identified by its client ID in the last couple of days. Okay, and we had to keep the statistics table on the left side up to date. And the baseline was just simply writing the statistics information before reading the values. And we had now write capacity unit for the DynamoDB table on the left side and read capacity unit for the key value store table on the right side. Okay, this had to be matched. This had to be equal. So we were spending more money unnecessarily because the statistics table had to be kept up to date, and same number of transactions went into both tables. We try to use auto-scaling. Okay, auto-scaling dynamically is changing these write-read capacity units for these tables, but there was a window that you can see on the right side that's shown by this red dotted line when the database was throttling. So the traffic came in, which was quite bursty. One of our misbehaving clients was just consuming 15,000 values or 15,000 keys and just banging this values endpoint 15,000 times, sequentially just going through these keys. And the scaling that you can see, which is this orange line, was not able to catch up because these requests were so bursty. It just tried to scale up, but until the scaling event happening, well, these requests were already gone. So first challenge we wanted to solve, reduce the write capacity unit. We don't keep the statistics table so up to date, but we wanted to spend less actually for writes. Okay, let's separate the critical path. There was a simplistic approach. We just simply moved the writes to another thread, not caring about if they succeed or fail. And they were using single thread executor for the implementation. It's hard to spot actually what was the problem based on the implementation if you look at the Java code. For this case, let me zoom in. Problem was that it was using an unbounded queue. So many multi-threaded libraries in Java by default use unbounded queues. And actually, it's not even an unbounded queue. Queue is just a very large queue. So getting back into queuing theory, if your queue is getting bigger and bigger and it has like an unlimited capacity or a very large capacity, your memory consumption will increase because you have to keep those requests in memory. And also your latency will be just skyrocketing after you have a very large queue because nobody will get being processed at the end of the line, right? So the side effect from that was quite simple. The container orchestrator was just simply killing and restarting the containers because they were hitting the memory limit. Okay, now we had one additional iteration, try to make our life simpler. So we've wrapped up this processing into a circuit breaker and a bulkhead. The bulkhead had the capacity limit for the queue around 20 requests. And the circuit breaker was catching two things: when write failed from the DB side and when the bulkhead was full. And we needed the circuit breaker because there was a monitoring attached to that, so we were know when we need to stop writing because it's totally useless, and what also helped us to understand better when these strange scaling issues happen. And we were having an understanding of the frequency, but long story short, it helped us to actually reduce the write capacity unit finally for the statistics table without having any serious side effect. But really wanted to do something with the reads. Okay, and this is again just as a recap. This is what's happening. So if you have 15,000 items coming in, we have for the service an auto scaling group that just scales out and in when these burst requests arrive. And when the table capacity is reached, then it's responding as HTTP 400. That's coming from the DynamoDB that's showing that's throttling. Okay, we have the database auto scaling, but the scaling of the instances is much more responsive and has less issues. And the goal for this exercise is just introduce something that's backward compatible with the client libraries, because it was a shared responsibility. So we had to be backward compatible because we could not change the client library, unfortunately. That's going to just pause the request for a while until the auto scaling is catching up. So we have to do some sort of a back pressure that's backward compatible, and that's just waiting for enough time for the scaling events to happen. First thing that we can do, just retry. When there is an HTTP 400, we can just resend the request, keep that in memory. This will kill actually the wait time on the other side because we are just retrying. But also there's no fairness here, because if there's these 15,000 requests are coming in, the other clients have much worse performance metrics, just because these requests are choking our services. They are just retrying like crazy, trying the scaling event to happen on the other side. Built-in rate limiting is the other option. I think we tried resilience 4J. That worked quite well. It's very precise. The calculations are top quality. So they're producing stable values if you think about rate limiting. There is also in the library, there was also a way of applying rate limiting per API key. So it was ideal in our case. Problem was the auto scaling. So we had not had a fixed number of instances running. So in this case, for instance, you have 40 operations per second on each instance. Now the overall throughput which is allowed is 80 operations per second. If you scale out, then the rate limiting is changing. That's scaling up this rate limit setting. You need something that counting these values globally. Next thing you can do is do it on the service mesh. This also has rate limit settings. We were using Istio in this case, which is, if I remember right, using Envoy, which has a global rate limit setting. It's using Redis to count these to maintain these buckets that's doing the rate limiting. Problem here was the API change. So it was not keeping the requests and waiting for resources to be freed up. It was just simply responding an HTTP error. And that's a breaking change. We needed a client library change in this case, which, because it was a shared responsibility, was quite slow to push through. Okay, so now here comes queuing theory. You can use queues in this case, I believe, to just keep the request in memory, to separate each request type based on the API key and based on the quality of services. And we have 15,000 items to process. And this overall duration here that you can see for all the marbles has to be under 30 seconds, because that's the default timeout setting for all the client libraries, including this one as well, that was used. Now, if you do the calculation with 2 workers, with 2 executors, you have to process 15,000 items in 30 seconds. This leaves you with 500 operations per second. And that might not be the problem, because that's quite doable. It's not a large number, but the latency for each executor has to be 4 milliseconds, which is quite tight. It's a hard to reach number with the stack that we had. So remember again, latency, queuing, and the throughput are 2 different numbers. You should look at both. But if you do something like 5 workers, it seemed doable, because now the latency, even though the throughput is the same, latency can be increased around for 10 milliseconds. So we looked at RabbitMQ because it had some quite interesting features. For instance, it had many ways to negatively acknowledge the message. If, let's say, the DynamoDB was responding with HTTP 400, then we could just send back a reject or another negative acknowledgement, and the message was just sitting there waiting to be processed still. There was also an overflow setting, which I think we use in this case, and it was also showing, as was also offering, I think, rate limiting by default, but that was quite hard to control, because it was depending on memory and CPU constraints, and we did not need those. We just needed a specific number for rate limiting and apply it to each client. And the configuration of consumers is quite flexible, as you can see on the top right on the screen. So for each channel, you have per consumer setting, and you can connect to multiple queues. And that's actually what we tried in the sandbox itself. So the service had its own auto-scaling group, workers had its own auto-scaling group, and the workers actually attached to all the queues. And the queues themselves, as the defined configuration, were holding the rate limit. So that's how the rate limiting was global. So they did not really depend on the number of workers attached to each queue. If the queue hadn't had, if the queue overflow setting was already showing that, okay, it's filling up, then the queue itself was just had to wait until the workers were proceeding with consumption. Services had to wait while sending these messages to the queue for the response to arrive. Okay, but for the others, because they were separated by API key, the other clients, which were processed in a separate work queue, were able to proceed if there was enough capacity from the database. Okay, and this is how things were working based on measurements. So this is the direct read. It's showing 300 operations per second as the request rate. The response time was around 10 milliseconds, so that's why with 2 workers it was quite challenging to meet this 4 millisecond number. And on the response time distribution, this diagram is a bit messed up, but you can see that the response times are quite tight, so they just very close to 0, especially compared to the other example when we had a single worker. Now you can see with a single worker that the request rate now is around 150 operations seconds, peaking to 200 operations per second, but the whole processing window is increased. So now if I see it correctly, we have now 2 minutes of processing instead of just this very tight processing window. So that's how the back pressure is kicking in for the specific client, which is now sending all the requests. And the response time average is again, it's a bit higher because we are measuring it from the API and it has to go through also through the workers. But the distribution itself is now not very close to 0. It's much better distributed than in the previous case. But as I said, numbers are a bit messed up. And with 5 workers, we also had the measurements. You can see increasingly that now, if you can trust the measurement, there was also a case when the throughput was even higher than in the first case. So it peaked to 500 operations per second. But still, all the requests were processed much longer. So for the older requests, it took, I think, if I see it right, 30 seconds to process all these 15,000 keys. And the worker execution time on the bottom is again around 10 milliseconds, if we a bit above than 10 milliseconds. So showing that with 5 workers, probably this will work as expected. And the response time distribution stayed as it is. So even though we added more workers, it was still much more evenly distributed than in the previous case. Yeah, so I think time's up, and actually we are at the end of the presentation. So this is all that I wanted to say. I hope it was very interesting. Again, my name was Oresztesz Margaritisz, and I'm an Associate Chief Software Engineer at EPAM. And if you have anything related to this topic, then feel free to reach out to me using, it was Twitter, now it's X, writing a private message. If you're an EPAM employee, then even writing me Teams. I encourage you also to find my GitHub repositories in my profile. There are several interesting things there, including, for instance, an availability simulator that I use for these calculations that you've seen. Also an example related to this project that shows you this rate limiting, how it works with RabbitMQ. And if you're interested in any of these topics, then I have several links included in the references section. So just feel free to wander around and explore those topics that interest you more. Thank you again for listening and being here.
Thank you. Thank you very much for the great presentation, and thank you from the audience. I see a lot of comments, and actually some of comments are already questions to you. But firstly, I'd like to note for the audience that, guys, as you have already seen, the presentation is full of references. So the slides will be also attached to the speech below the video recording on the OrgJaCoVCommunity page of that talk. So you will be able to go through all of these links by yourself. And let's go to the Q&A part. So the first question is, what are the recommendations to reduce the effect of securing the communication channel and interactions?
The effects of, I'm not sure if I got that correctly. So what we are trying to reduce, sorry.
The effect of securing the communication channels. So since security protocol might also bring some latency and all of that stuff.
I understand that. Yeah, security is a heavyweight topic, so it's very hard to just pick up something that can be done all the time and just mention that like a magic solution for all your problems. Yeah, so securing the channels. You have to think about how it slows down your communication, how many ways it's affecting the performance, because there are not just one way of doing that. So security, as you're talking about encryption, also probably has a CPU related implication. So it needs some processing power. That's the least issue, seems like, because locally processing something and calculating something, if the data is already there, then should be easy to solve. Um, Another negative implication of security is connection establishment. So if you think about SSL, for instance, then building up an SSL connection takes way more time than just not doing that, because if you zoom into the protocol, probably you will see things like symmetric key generation, sharing this key for for that simple communication channel. When it's closed up, then you have to do it again, and so on and so forth. So if you think about securing in terms of HTTPS, let's investigate this situation, then you can keep the connections open. As far as I know, there are SSL termination mechanisms which are doing that, helping you not to have to request the same SSL connection and build it up from the ground. There are also other protocols which are not HTTPS based but still using SSL, which by nature leaving this connection open and not building up from scratch. So if you go through a messaging broker, then you don't necessarily, even if you are doing a secure communication, you don't have to do it from scratch. So I would look at SSL termination, probably having permanent connections, choosing a technology or a library that allows you to do that. I don't know if there's any other use cases. That's what I can come up with in brief right now, but probably there are plenty of them.
Sure, I totally agree, and basically we always need to like keep the reasonable balance between the speed and performance and response time of our application, as well as the security measurements which we need to maintain. So as for the other questions, how can we balance the need for rapid deployment with the need for reliable communication between microservices?
Question is that have you had to sacrifice anything related to reliable communication and rapid deployment? If you have to. I mean, I think in the current state, there are many sophisticated libraries, technologies that are having that help you actually do a gradual rollout, fine tune it, and not to have a significant effect on the architecture itself. So I remember in several times we deployed so complicated things and were surprised that it's not really affecting the clients at all. That was very surprising. So in brief, well, I say that it should be just a matter of technology choice, because the automation can react much faster than you will be reacting, and can do it on a lower level. Um, on higher level, if you really want to do something drastical and you are afraid, then it's not rapid deployment. I mean, then you have to do it on a much slower pace. If it's affecting your data, anything like that, then you have to do it in more gradually and with a manual intervention. Look at your metrics and draw back if there's a problem. You have to calculate the risk. What I encourage you to look at is probably site reliability engineering and taking risks. So you have to have a baseline, like, I don't know, 99% of availability that gives you the number of error you can spend actually as an error budget. I think that's how it's called. If you are aiming for something higher, then you are not taking enough risk. If you are performing worse than that, then you have to go up towards stability. So that's how I would address that. You don't have to go for extreme numbers. That's not ideal.
Yep, and I think one of the like key points in order to find this right balance is clearly understand your infrastructure. So as much as it possible, taking into account any possible complexity of it. So clear understanding of interactions between the services and so how they affect each other definitely will help you to find the right balance and the right places where you can, for example, slow down the deployment and where you can, for example, sacrifice so some of your reliable connection or so speed of this connection. So this is clearly important to understand how exactly the whole microservice infrastructure works.
Yeah, you have to be practical. I 100% agree. Yeah. First is just pressing the button, but then you have to learn the hard way, right? And have to
Yeah,
improve.
exactly. Yep, and one interesting but kind of abstract question. What are your thoughts on the future of microservices architecture?
Yeah, so what I feel like now is that the future, so there are many ways to optimize even further what we have, but I feel like we reached into this maturity stage after so many years that makes it accessible to basically most of the people who would like to use microservices. So I think what's happening is that this hype cycle is over. So microservice is not an obvious choice, fortunately, for every use case. So probably people will be more conscious about their decisions, and there will be less microservices around. And that's probably a positive change because it can be very tedious, working with all these resources, these extreme numbers, and just people, some cases just feel like it's just a race to just deploy hundreds and tens of thousands of things at once just because we can do so. It's just burning money and not doing anything really in some of the situations. So I think it will be the next couple of years, maybe more humble, maybe. AI is coming, so that's probably taking all the light from microservices in the next years.
Yeah, the next tool set which will be applied everywhere. But yeah, my beloved proverb regarding this is that we can hammer nails with the microscope, but the question is in effectiveness. So
Yeah.
actually, yeah, for the microservices, I could say the same. So the question is in effectiveness, and it's actually really important. I totally agree that it's great that the microservice architecture reached such level of maturity. So a lot of people know about the actual microservice patterns, and the number grows and grows. And developers have started to study this from the very beginning of their career, like together
Yeah.
with the regular design patterns and all of that stuff. And this definitely brings like the better understanding of where it makes sense to apply the microservice architecture.
Mhm.
So that's why I also agree that it possibly might not be like so hyped and overhyped again, but it will become like our daily routine and the important piece of work, the regular one, and the one which is going to go with us into future, definitely.
Yeah, maybe it would be worth talking about the dark side of microservices,
Mhm.
because it's very strange for me that I've met, for instance, some engineers having a couple of years of experience, which were working only on aggregated services, and they were complaining that they had no experience working with databases, and that's something that was very surprising me to see, that things change so much that there are coming a new generations of developers who are struggling with working with data just because they were just firing up REST calls after one another in a microservice architecture for years. Yeah, so that's something not to forget. Yeah.
Yep, it's always necessary, like to keep in mind all of what's happening inside the like tool set you work with. Yeah, and it's sometimes difficult to focus due to the like trends for particular technologies. So to keep on track with the other ones which are also a part of our regular work.
Yeah.
By the way, one more question from a chat. To understand the context of examples in the presentation, what was the scale of solutions presented, especially those with DynamoDB, in terms of daily or monthly active users? Thank you.
Yeah, it's for the DynamoDB use case, you cannot transfer that to daily active users. I mean, the whole architecture that we were working on, um, we're handling people at a global scale probably, but the usage patterns were not translating into this specific service that we were, for instance, fine tuning, because it was sitting on a very lower layer behind all the other services. So we've just seen some synthetic kind of request patterns, mostly related to services starting up or restarting in periodically or refreshing their caches proactively. So interesting thing was that the daily active users were not affecting us in this specific case. For other cases, I don't know, craziest number that I've seen was just, I think, 1,000 instances, but I don't really remember. Maybe that I'm wrong about that. It was roughly 1,000, but this was just a specific service and its auto-scaling configuration. So usually a single team works with no more than 5 to 6 services, and these access patterns really depends on where the service is sitting. For us in this lower layer, because it was part of, let's say, platform layer, if we have um, an outage that affects all the clients, it's not critical, it's not on the critical path, so you can still, for instance, use the shopping and paying functionality, but from the user's perspective, from user experience perspective, let's say it's visible, but not performance was or critical measurement. It was more like the uptime, which did not have really an issue because it was working very stably. I don't know if it answered the question, but the interesting thing is that you cannot really, um, it's not always user facing, and it does not really determine you. So just throwing it in a large number does not tell you the whole story, I think.
Yeah, definitely. So, in general, sometimes it's not so clear which exact load in like users per day or users per minute might bring the load for the whole system more or less significantly, because basically a lot of process inside all of that infrastructure might like process a lot of calls, a lot of retries, as we have already discussed. So basically, sometimes the like overloaded systems might occur just because of some error or just a mistake in the logic of work for the whole infrastructure, and it's not so critical to like have the high load at that moment. So it's really important to think about the architecture in total, and definitely it's important to make it as more effective as possible. So regardless of the particular load sometimes, but still like keep the balance between the efforts which are applied to that and the effectiveness of the solution. So I think that it's great to like understand all the possible approaches and to choose the right and the most effective, cost effective as well ones for that purpose.
Yes, exactly.
Yeah. So I don't seem to see any other questions, but guys, I give you like possibly 2 minutes more. I'd like to add one more question from me. Oresztesz, you mentioned a lot of services, a lot of libraries. Some of them, if I got it right, were so inside the AWS infrastructure. But if I got it right, AWS itself has a lot of services which also might kind of be replacement of the open source one. So, for example, they have their own app mesh as a service mesh solution. They have some tool set, for example, for the load balancing and stickiness to the region, and so a lot of patterns implemented inside the infrastructure. So, from your standpoint, is it better to use some services provided by the vendor itself, or like to rely on the internal implementation or like your own custom implementation of some services and some patterns?
Mm-hmm. Yeah, so own implementation is something that you have to be very careful with. I think that's the part where you have to be the most careful, because that's the last kind of last decision that you find a decision that you have to make. So first you have to understand if there's something you can pay for that's already there. Maybe there is an open source solution for that. And if you cannot find anything at all, then maybe do something that's cheap and rough, but still shows you how much effort are you looking at. So if AWS is something that you should use or not, what I can answer is that in most of the cases, the technology choice is already done. So we were not using service mesh just because we wanted to or something like that. That was already in place and already part of the portfolio. If you have the option to use something, again, most of the cases it's depending on your scope. So if you are just a small team shipping features, you won't probably choose something that affects the whole global infrastructure of thousands of services. That's not at your level. So that's probably, again, at platform level. Several platform teams will work on to roll out this solution. The migration effort has to be considered. So it's a very complex choice. That's why, for instance, in this case, when we are using RabbitMQ, we chose something that was applicable locally. So that has small infrastructure cost. That's a very special solution, but we haven't found anything that was that we were able to use. And also, the configuration again was special, so we had to manage our own configuration, unfortunately. So if there would have been a managed queuing solution that provides the same usage, then I would have probably gone with that, because managed solution, of course, has less maintenance cost. So by default, I think a managed solution or platform as a service is the ideal choice if you are sitting on a feature team, because you don't want to maintain the whole thing for everyone, for the whole organization. Yeah, and if you are lucky enough not to do so, then it's a much slower kind of development, because it has to be gradually rolled out. You have to think about the rollout phase. No team is going to just do it in the next week, and you have probably hundreds of teams to work with. So that's a whole different story. Yeah, in brief, I don't know if you answered your questions. This is the main difference that I see. It depends on many things.
Yep.
I mean, I could mention, for instance, vendor lock-in. So that's something that's you have to be aware of, but many of the tools like the managed Kubernetes services probably don't have so many differences between each other.
Yep, especially in case if we apply something like infrastructure as code solutions like Terraform for deploying all that. Yeah, so this might significantly simplify either migration from one cloud to another or building like multi-cloud infrastructure. So, but anyway, yep, I at least I see the trend from each cloud provider to build up their own solutions, their own like simplified wrappers for their own solutions. So to encourage us to apply their particular infrastructure approaches like as a service without any particular adjustments. So they invest more and more in making their solutions more like resilient, more fault tolerant, build up the patterns which we so earlier needed to implement manually a part of their own services. So that's why sometimes it might be also a good solution and a good option to consider. So, yep, I think that's all about the questions. So thank you very much, Oresztesz. Guys, in case if you if you wanna rewatch this recording, let me remind you that the recording will be attached to our OrgJaCommunity page of the talk. Also, you could use this page to say your thank you for the speaker. There is a separate button which allows you to send the hero badge right from the OrgJaCommunity platform to our amazing speaker, as well as you can rate our talk using two separate options or both of them at the same time. You can rate the talk on the talk page by the stars below the page, and also you can leave us your feedback. We always happy and always open to any of your thoughts on our events. And in case if you want to become a speaker for the JACOV community, please do not hesitate to contact us. All the contact links can be found on the OrgJaCommunity platform page. Also, many thanks to our partner community for this event. Let me possibly share the link to it. Actually, the link will be also attached to our OrgJaCommunity page. So Budapest Java community, many thanks to you as well. Guys, see you soon on our further events. Thank you very much.
Thank you.